Good afternoon, everyone. My name is Aldrich, and today I'm going to be making a podcast, which is something that I rarely do. You see, in school, my teacher told me to make a project for school, so I chose making a podcast. So, in today's podcast, I'll be discussing about the history and the discovery of pi. So, if any one of you haven't known, pi is a very important mathematical constant. Pi is an irrational number, or even some might say it's a transcendental number, which can be derived from the ratio of circumference of a circle to its diameter, which is why the formula for the circumference of a circle is pi times diameter. However, that's a very bland and rough explanation for pi, because not many people appreciate pi, because essentially, pi can be said as the backbone of many different math subjects, from Euclidean geometry, analytical geometry, even the advanced calculus, finding areas of curves, and etc. Pi is very important in all of these. And even more, not many people appreciate the fact that pi is an irrational number, having decimal digits up to infinity. Moreover, people don't really realize that we don't really have an easy and plain sailing way to figure out digits of pi to thousands of digits without using computers. Nowadays, we take it granted that pi is equal to 3.14 and so on. However, how do we use to calculate pi? Well, in this podcast, I'm going to discuss about Archimedes' method and innovation about calculating pi. In my next podcast, I'm going to be discussing about Newton's way, how he revolutionized the whole history of pi. Well, the first thing that I want to discuss is the method called bisecting polygons and hexagons, which is the method that has been used over 2000 years. This method, though, was painstakingly hard and takes ages to calculate. However, this is still very important to the history of mathematics, and even without this method, I don't think that the mathematical society will reach how it is today. This method was developed by Archimedes. So first, we can take a simple unit circle. A unit circle is basically a circle that has a radius of 1. And then, we can draw a hexagon inside the circle, where the corners of the hexagon touches the sides of the circle. So there's not that much gap between the hexagon and the circle. So we can easily calculate the side of the hexagon to be 1 unit. Why? Because if you haven't known, if you have a hexagon inside a circle, the side of the hexagon is equal to the radius of the circle. However, if anyone of you want to know more explanation of it, well, you can just divide the hexagon into 6 same equilateral triangles. And if you look at it, the sides of hexagon will be equal to the side of one of the triangles, and the radius of the circle is also equal to one of the sides of the triangle. So we can deduce that they are both equal. So now we have found out the side of the hexagon, so we can easily figure out the perimeter of it, which is 6 units. Because hexagon has 6 sides, so 1 times 6 is 6. So why is this important? Why is finding out the hexagon's perimeter going to be useful? Well, just think about it. If you have a hexagon smaller than a circle, then the perimeter of the hexagon is going to be less but close to that of a circle. So we can use the circumference of the hexagon to approximate pi. So we can already make an inequality that the circumference of the circle is going to be larger than the perimeter of hexagon. So what is the circumference of a circle? It's 2 times pi times r. The radius is 1 because it's a unit circle, so it's going to be 2 pi. And on the perimeter of hexagon, we have found out to be 6. So 2 pi is larger than 6, meaning pi is larger than 3. So we have already figured out a pretty good approximation of pi. Pi is larger than 3. However, we can also do another method, which is actually using the same exact steps, but rather than finding out a hexagon less than a circle, we find a hexagon larger than a circle. So we also can figure out the maximum amount of pi. So now, let's say that we have a square, let's say, surrounding a circle. And because the square must not be that big, we can make the side of the square equal to the diameter of the circle, so that it won't be too big for approximation of pi. So then we can do the exact same inequality, the circumference of square, this time being larger, the circumference of circle. We do the math, we substitute for pi, we isolate it, and we can figure out that pi is smaller than 4. So now, through this simple method, we have figured out that pi is in the range of 3 until 4. And nowadays, we know that this is very true, because pi is 3.14. It is inside that inequality. However, how will we find more exact measures of pi? How can we figure out pi up to hundreds of decimals? Well, now we can enter Archimedes. So, Archimedes soon improved the method using even more complicated shapes. For example, before we have used hexagon and a square, which is rather easy to calculate but not very precise. So, Archimedes used a 12-sided shape, which is called a dodecagon. And now he can also use the exact same method, and then he can figure out the approximation for pi. This method was very hard and take ages to calculate, especially if you start using even more complicated shapes. However, this was still very useful at those times. So he calculated a shape with 24 sides, and then 48 sides, then 96 sides, and when he reached 96 sides, well, he stopped, because at that point, calculating it would be way too hard. And at that point, he figured out the value of pi to be between 3.29 and 3.1429, sorry, and 3.1408. Rather precise, because we know that pi is 3.1419, but it was not precise enough. So, for the next 2000 years, everyone had been using this method to figure out values for pi to higher and higher precisions. However, as I said before, this method is very tedious and is very long to calculate. And by long, I mean really long. In the 17th century, the Dutch mathematician Lodolph van Ceulen calculated pi using a polygon with 2 to the 62 power of sides. 2 to the 62 power. It's not 62 sides, it's not 2 sides, it's 2 to the power of 62. That's over 4 quintillion sides of polygons, all calculated by hands, without computers, without anything. And what was the level of precision of pi he calculated? Only 35 digits. 35 digits. And he took 25 years to calculate that amount of pi. So, although this method may not be the easiest and the fastest, this method is the only known one at the time. So, even though it's a painstakingly hard chore to calculate n-gons until quadrillions of sides, they still did it. But actually, all of that calculation for more precise values of pi wasn't really needed at the time. The scientific society was okay with some 5 to 10 correct digits of pi. At that point, it was only to flex their arithmetic skills. However, they still did it. Why? Why would they devote their whole life to only show their mathematical skills? Well, it's because to them, it's more than flexing their skills. It's more than showing their expertise. To them, it's about advancing the scientific society. To them, it's about advancing the mathematical civilization. And for that, we have to appreciate them for their hard work. Thank you for listening. My name is Aldrich, and have a great day.